Welcome. In today's video, we're going to derive the mean and variance of the uniform distribution. So to begin, let's remind ourselves that if a random variable has a uniform distribution with parameters a and b, where a and b are the endpoints, then the PDF or the probability density function of that random variable x is given by the following. F of x is equal to 1 on b minus a, and that is true for x is an element of a to b. And if we were being, I suppose, a little bit more pedantic, we would say that 0 elsewhere. And that'll come in handy when we do this, or when we calculate the expected value. So the expected value of x, and we define that as, in this case, it is a continuous distribution, so we need to use the integral definition. So it becomes the integral of x in the sample space of x multiplied by the probability density function integrated with respect to x. And in this case, it's pretty straightforward. In this case, x takes values we already discussed from a to b only. So our integral only goes from a to b. And we also have our value of x, and then we also multiply that by the probability density function, and then of course we're integrating with respect to x. Now, in this particular instance here, note that 1 on b minus a is a constant with respect to x. So when we integrate, we really just need to focus on the integral of the first, that x there. And when we do integrate x with respect to itself, remember we add 1 to the power divided by the new power. So in this case, the power, I guess you could say, is 1. And so adding to the power, you get 1 over 2, 1 over the new power, x squared, and then we're still multiplying by the constant. And then, of course, we're going from values from x equals a to x equals b. Doing a bit of substitution here, what that ends up being is a half b squared multiplied by 1 on b minus a minus a half a squared multiplied by 1 on b minus a. Now I'm going to express this a little bit more nicely, and when I say nicely, I say, well, we've got a factor of 1 on b on a as a common, 1 over b minus a, sorry, as the common factor. We've also got a half out as a common factor. And in fact, what we can even rewrite this as b squared minus a squared all over 2b minus a. And here I've really just pulled out that common factor of the half and the b minus a. And then I've left with my b squared and my a squared here. Now, importantly, what we can do here is we're actually going to use something we're hopefully familiar with, which is the difference of perfect squares. So here, b squared minus a squared, we can rewrite as, b minus a, b plus a over 2b minus a. And then that can simplify down to simply, because we can cancel out the b minus a here and the b minus a down the bottom, because they're non-zero, because b and a are not the same. Then we can simply rewrite this as a plus b on 2. And so there is your expression for the expected value of x. Now that we've come up with an expression for the expected value of x, we're going to calculate an expression for the variance. Now, the variance, the first thing we need to be aware of is how to calculate the expected value of the second moment of x, and then we'll use that to find the variance. So let's begin with the expected value of x squared. And again, by definition, what this means, it is the integral where x is in the support of x, or the sample space of x. In this case, it's x squared multiplied by the probability density function and integrated with respect to x. So if we do this calculation or this substitution, again we have the integral going from the terminals being a and b, a to b. We've still got our x squared, and then we're again going to multiply by b minus a as the probability density function, again integrating with respect to x. And again, now we're going to integrate, and this is simply a power. So when integrating with respect to a power, we add 1 to the power, so that would become 3, and then divide by the new power. So in this case, it becomes 1 on 3x cubed, and again, it's just multiplied by the factor because that factor is a constant with respect to x. And again, we've got the terminals a and b on the side. Next, after this, we perform our substitution. So in this case, our substitution will be 1 on 3b cubed multiplied by 1 on b minus a minus 1 on 3a cubed times 1 on b minus a. Wherever you see the x cubed, you replace it with the two terminals and subtract the two terminals, as we've done here. Now, we can do again, similar to the previous example, we can take out common factors. In this case, there's a common factor of 1/3 and 1 on b minus a. And then we can express everything in the numerator, so it becomes b cubed minus a cubed on 3b minus a out as the common factor. Now, similar to the difference of perfect squares, there's also an expression for the difference of perfect cubes. So with perfect cubes, b minus a actually has the expression b cubed minus a cubed has the expression b minus a multiplied by a squared plus ab plus a, or plus b squared, I should say. Or let me write it in maybe in a format which makes a bit more sense. It'll be b squared plus ab plus a squared, just to, I guess, keep some order about things. And then again, that is 3b minus a. And again, nicely, we have this function cancelling this b minus a, or this expression b minus a cancelling with itself. And so now what we have left is a squared plus ab plus b squared over 3. Now, we're not done just yet because this was only the expected value of x squared. We're going to use the we're going to calculate the variance now, and the variance, the expression for the variance of x, is equal to the expected value of x squared minus the expected value of x all squared. Here we just derived our expression for e to the x squared above. So we're going to put that through. We're going to put a squared plus ab plus b squared over 3. And then we've got minus, we've got our expression here, a plus b over 2 for x squared. So it becomes a plus b over 2 all squared here. Coming up with a little bit of, or some simplification, what I'm going to try and do is I'm going to try and combine these two particular fractions together. What we'll have here is a squared plus ab plus b squared over 3. That doesn't change. However, this side part we'll expand the a plus b squared at the top. So that would become a squared plus 2ab plus b squared over 4 in this particular instance. Again, we're still not done just yet, so I'm going to take this, copy it to a new page, and I'll put it at the top here, paste that in. And again, remember we're solving for, trying to calculate the variance of x. So when we have two fractions, or we have two fractions that are subtracted from one another, what we can do to put them under the same sort of bracket, and this is just a side note, if you've got a over b minus c over d, you can actually do this sort of cross multiplication where you've got ad minus cb over bd. And that's effectively what's really happening here in this expression that we've got here, is we're just putting something over the same denominator. So in this case, the lowest common denominator. So in this case, where we've got 3 and 4, the lowest common factor in this particular, or lowest common multiple, apologies, factor's the other one. Lowest common multiple between 3 and 4 is 12. So if I just put this back here, to turn this into an expression, we've got 12 down the bottom here minus something over 12 down the bottom here. To turn the 3 into a 12, we need to multiply the numerator by 4, or we need to multiply the numerator and the denominator by 4. So you've got 4a squared plus ab plus b squared. And then, of course, similarly with this case where you've got, again, to get 12, we had that lowest common multiple between 3 and 4 is 12. So to get 12 on this side, what we needed to do to go from 4 to 12 was multiply by 3. So we're going to do the same thing to the numerator here. So it'll be 3a squared plus ab plus b squared. And again, let's do this. Let's do some simplification, or some expansion and simplification. This will become 4a squared plus 4ab plus 4b squared. And then we're subtracting everything on this side, and that becomes minus 3a squared minus 3ab. Apologies, I've forgotten the 2ab in the middle here, so it'll actually become 6ab. I've made a bit of an error there, but hopefully you can see that now that should have been 2ab. And then we've got minus 3b squared at the end. And again, this is all over 12. After this little expression, we note that we've got 4a squared and 3a squared here. So that becomes a squared when you subtract them. We've got 4ab and we've got a minus 6ab, that becomes minus 2ab. And then as well, we've got 4b squared and we've got a minus 3b squared here, so that becomes a positive b squared. And again, still over 12. And then of course some people like to sort of simplify the top here, noting that this actually happens to be a common square where you take in this case, I'm going to write it as b minus a all squared over 12. And that, ladies and gentlemen, is how we calculate the variance of the uniform distribution. So here is the expression for the variance, and if you've already forgotten, here is the expression for the mean down the bottom.